Good morning. I hope you all had a great weekend. I sure enjoyed meeting all of you last week and stuff, and slowly getting used to all of you and stuff. It's so cool to be with people. Before I start talking about like what's happening today or start lecturing, did everybody's experience Mount Hood go okay last week? Were there any questions that you had, or? Cool. That's awesome news, actually. All right, so this week, what's going to happen? This will be more like a regular week. And on Wednesday at 8 o'clock when we get here, there's two things that you should bring with you. And the first thing you'll turn in like right away, and it's called the 8 Bottles Lab, the one we did last Wednesday. Should be pretty chill. The other thing, though, that will be due, but you'll hold on to it, will be problem set number 1. And ideally, before Wednesday at 8, I'd like you to try the problems, all right? Just go through, see how you're doing, stuff like that. And then our time on Wednesday, that first 2-ish hours or so, what we'll do is we'll then go over problem set number 1. And I want you to ask questions on it. I want you to see what's happening, stuff like that, before you turn it in. If you've been watching the online class, I make a big deal about making sure that you self-correct your work. So instead of just listening to me babble on about problem set 1, I do want you to actively grade your problem set, so make marks when things are right. And if something is wrong, it's definitely not a big deal. Just make sure that you self-correct and stuff. You'll turn the problem set in, it can have marks all over it, and you'll still get full points. And I actually love it when people mark it up pretty heavy. So it should be pretty chill. Also, I didn't put up here, but you should also bring a printed copy of the density in class version lab on Wednesday. I forgot to mention that. After we talk about problem set number 1, then you'll turn it in, and we'll go upstairs and do a lab. This is the density in class lab. It is different than the density online version, so make sure you have the in class one. But we'll actually use the scales, do some volume mass measurements, stuff like that. Okay. And then also this week, by Wednesday night, all right, I'm hoping Wednesday by 6 p.m., but I'll say Wednesday evening, I'll release quiz number 1 to the website. And right at the top, and there'll also be a link in Discord and stuff like that, there'll be a link for quiz number 1, and your goal is to download it and complete it, and then email it to me in PDF form by Friday at 9 a.m. And so it should be pretty chill. So Wednesday night through Friday morning at 9 a.m. Is when the quiz will be due. Are there any questions? Any of this kind of stuff? Awesome. Well, I really do enjoy having you here. It's so cool to have people I can't even begin to tell you. So thanks for being here. I'm going to do just a little bit more with chapter 1 before we go on to the next section. So I'm going to backtrack a little bit from what we did on Monday. And on Monday at the end, we left off with the sig fig stuff. So I'm going to go back just a few slides and talk about some of the more important parts about significant figures. Sig figs are really probably the most important part of chapter 1. It's probably the most boring, so I apologize in advance. But it's something we'll use over and over and over again. And this kind of problem demonstrates why it's important. Because let's say that your car travels 278 miles, and it takes up 11.70 gallons of gas. The question is, what's your gas mileage? The calculator will give you a lot of digits, all right? So in the calculator, before I got bored writing them in, 23.76068. And in science and in all the experimental-based sciences, we try to limit the number of significant figures reported based on the types of measurements that went into it. So in this example, all right, it was a 3 sig fig number. 278 has 3 significant figures. and 11.70, and the 0 after the decimal and after a non-zero digit does count. That would be a 4 sig fig value. So you can see here we've got 3 sig figs on the top, 4 sig figs on the bottom. When it comes to determining the number of sig figs we can use in the answer, we use the smaller number of sig figs, which in this case is 3. So going down here to the number, you go 23.7. That would be 3 sig figs right there. But before you just get rid of all of these numbers, you do look at the first digit that you're going to drop. All right, you don't look at the other ones. You could care less about the 068, but you do want to look at the first one. And if that first digit dropped is between 5 and 9, then you round up the last digit by 1. So you can see here the answer is 23.8. If the first digit dropped, it would have been between 0 and 4. We would have left it at 23.7. On the other hand, if it's between 5 and 9, and we're going a little bit away from what the textbook does here, we're making it simpler, honestly. If it's between 5 and 9, then you do round up. So this would become 23.8 miles per gallon. And that's really all there is to sig figs when you multiply or divide. And the good news is that most of the time in chemistry, that's what we do. We multiply and divide. When we do density or when we do mass and volumes and stuff like that, it's usually multiplying and dividing. And people usually do pretty well on this. So are there any questions on this process? The addition and subtraction is something that pops up, and it pops up mostly when it comes to temperature, because as we talked about, most of the time in lab, we'll record temperatures in Celsius, but for calculations we use Kelvin, so going between Celsius and Kelvin is that 273.15 number. So these rules we won't use as often, but when they do pop up, there's a separate set of sig fig rules, and that can be kind of confusing at first. And so in the example we looked at last Monday, we were taking 3.18 liters and adding 0.01315 liters to it, okay? Now your calculator will give you this number right here, 3.19315, and that's fine. However, the problem comes when it comes to experimental analysis is that whoever measured this value, all right, they didn't go very far, at least relative to this number. So we don't know what the question mark values are. If we're lucky, they would be 000, all right? But that's not a very high probability to be 000. Probably it'll be something else. And all of those something else's then would add to that 315 to make different numbers down here, all right? So we don't know what those question marks are. So when it comes to adding and subtracting, that's where we really get into this doubtful digit. And that's always the last sig fig of any number. So in 3.18, it's the 8. In 0.01315, it's the 5. All right, it's always the last digit. And the idea is you cut the answer off at the larger doubtful digit. And the 8 is at the 10th position, all right? And that's bigger than the 5, which is at the 100,000th position, i.e. you pick the one which is most to the left, all right, if you're doing this. So the 0.18 is 2 to the right, the 5 is then, I think, 5 to the right of the point. You want to pick the one closest to the left. So notice here this little dotted line. I'll use this sometimes when talking about adding and subtracting. And we want to cut this number off at that largest doubtful digit. So we're going to cut it off there at the hundredths. 3.19315 means we cut it off after the 9. We do look at the first value that was dropped. This is a 3, it's between 0 and 4, so we don't do anything. That's why we left it then at just 3.19. So again, we don't do this as often in chemistry. It's mostly about temperatures, I'll be honest, temperature conversion. Sometimes like volumes being added or subtracted like in the lab this week. It's more rare, but it does pop up, and it's a different set of sig fig values. It's not as simple as like 2 sig figs and 4 sig figs making, or 3 and 4 sig figs making 3 sig figs. What you want to do is make sure you cut it off at that largest doubtful digit. Any questions on that? Okay. We'll do some of this stuff, of course, in the problem set and stuff on Wednesday. All right, you may need to round off your answer, and like I said, if the answer, the first digit dropped is going to be the one you look at. So if the first digit you remove is between 0 and 4, you just leave the number alone. But if it's between 5 and 9, then you add 1 to that doubtful digit, that last sig fig that you're going to keep. So 2.4271, if we were going to round it up to 2 sig figs, that would be 2 and 4. We'd have a little line there after the 4. And the 2 is the first digit you drop. 2 is between 0 and 4, so we leave it alone. 2.4 would be the right answer. On the other hand, if that first digit you drop is between 5 and 9, then you're going to round up. So 4.5816 to 2 sig figs, we cut it off after the 5. The first digit that we drop is 8. That's between 5 and 9. So 4.5 becomes 4.6. And again, the textbook does weird things when there's a 5. When you look at it, just ignore that. That's ridiculous. If it's between 5 and 9, go up. If it's between 0 and 4, leave it alone. This is an amazing textbook that it does that, but that's okay. Everything does. Anyway, babbling. Questions? So here's a question. Which one of these are round this number to 3 significant figures? Okay? And again, what we want to do is just cut it off. We need to know where the sig figs start. And these initial zeros right here, like we talked about, are placeholders. We need to know where the 3 begins on the number line. If we put this in our calculator and convert it to scientific notation, it would say 3.035 times 10 to the minus 3. So all of those zeros went away when we turned it into scientific notation. That's a way to tell that all of those are just placeholders. So we don't worry about these zeros. First sig fig, second sig fig. The 3 here is the third sig fig, so we'll draw a little line after the 3. The first digit we're dropping is a 5, and again, in our Chem 221 through Chem 223 rules, 5 to 9 means to round up, all right? So 0.00303 becomes 0.00304. That's all the rules, that's all there is to it. Questions? A mass percentage is something we'll use on occasion in chemistry. And it's a pretty simple concept, but I find that sometimes percentages make people a little bit nervous, and I don't want you to feel that way. So let's say that we had a compound that was 30% lead and 70% oxygen. Then all that means is that in 100 grams of the compound, you would have 30 grams of lead and you'd have 70 grams of oxygen. That's all that means, all right? And you don't have to use 100. You can use 1 gram. That's fine. So 1 gram would be 0.30 grams of lead, and 1 gram would have 0.70 grams of oxygen. And if you had 5 grams, you could multiply it by 0.3 to figure out how much lead was there, and 5 grams times 0.7 would tell you how much oxygen, this kind of stuff. That's all it means, all right? These numbers are just kind of them. And percentages, by the way, are something that we will apply significant figures to eventually too. You can have good percentages or bad percentages and stuff, so. Here's an example that's a little funky. Penicillin F is one of the antibiotics and stuff that's used sometimes for things. This is the structure. I thought that was kind of a cool structure. But anyway, I digress. Penicillin F is 53.829% carbon. So the question is here, if we had 75 grams of penicillin F, how many grams of carbon would there be? And again, it's pretty chill. There's different ways to do this. What a lot of you will do is just basically to take this number and divide by 100. So that would be 0.53829. And that number you can multiply by 75 to get the answer, and that's cool. If you're having trouble with percentages, then when you see something like this, that means 53.829 grams of carbon in 100 grams of penicillin F. So if you start with grams of penicillin F, you can do essentially a factor label. Grams of penicillin F on the top, 100 grams of penicillin F are 53.829 grams of carbon. The grams of penicillin F cancel, you've got grams of carbon. Anyway, any of these ways are totally cool. I use this latter method in this problem. Again, these percentages just mean for carbon here that you have 53.829 grams of carbon in 100, exactly 100 grams of penicillin F. So you can take your 75 grams of penicillin F. Remember, we want some kind of unit to cancel. So the grams of penicillin F on the top that we start with will be canceled with grams of penicillin F on the bottom here. Grams of carbon will be the only unit left, and that's what we're looking for. So in your calculators, 75 times 53.829 divided by 100 will give you this number. You could also take 75 and multiply it by 0.53829, and you get the same value. This number is a 2 sig fig number. We're multiplying and dividing. So the number that the calculator gives, we'll cut it off after the 0. We need to tell each other that that 0 is a significant number. 40 without a dot would look like a 1 sig fig number. So if you see the dot right there, that's just a way to show that the 0 is a significant number. It actually means something. So this thing has 40 grams of carbon. Questions on that? You can do a volume percentage, which would be like 3 milliliters of HCl in 100 milliliters total or something like that, but they're very rare in our classes, all right? In other kinds of classes, you might see them. So 99.99% of the time, all of our percentages will be mass-based. So in 100 grams of compound, you have this much carbon, that kind of thing. Cool. All right. So this is actually the formal end of chapter 1, and I just wanted to go over some of these last minute there's also some dumb graphics just to hopefully make you smile, but anyway, in the website and stuff like that, on the website, there are several types of guides that may or may not be helpful to you, all right, and it's absolutely up to you if you wish to use these or not. A study guide is a bulleted list of the concepts from these chapters that I thought, when I looked at it, are important, all right? So if you're uncertain, like you're feeling good, but you're like, oh, did I miss anything? The study guide would be something you can go through, and hopefully most of them you can just check off, you know. But if there was something in there, like, oh, I don't remember that, go back. Now, once in a while, I change the focus of my teaching. So if you see something that you don't recognize, absolutely email me, and I'll say, oh yeah, we're still learning that, or oh, maybe that's a dream I had one time but hasn't worked out. A concept guide, these are pretty cool, I think. These are a series of worked problems from each chapter. And so in chemistry, in chapter 1, like we saw temperature conversions, we saw density conversions and applications of, metrics, this kind of stuff. So the concept guide, all right, is nothing more than a series of worked problems. So if you're not sure how the temperature ones work, for example, you can go to the temperature conversions in there and kind of follow along, make sure you get the right answer. By the way, neither of these are anything you ever have to look at. They're just guides for you, all right? And if you decide to use them, cool. And if you don't, it's all right too. I do have what I call Chapter Guide 0, which is kind of like a math concept guide, a math overview of different things we'll use. Again, you can look at it, but you don't have to. In addition, and again, I won't do this for each end of the chapter, but after the PowerPoint notes are done, I do have a couple of extra slides. One of them, I'll show it to you here. These are what I consider to be the important equations, constants, that kind of stuff for the different sections. So in chapter 1 here, we saw how there's the 5 metric prefixes, which are really important. A centimeter cubed is equal to a milliliter. A significant figure is really important, mass percentages. Here's the density relationship. And there's the Kelvin to Celsius way to convert. Those are kind of what I consider to be the most important equations from these chapters, all right? So it's kind of a good way to, again, to make sure that you're up to speed. And then finally, at the very end, I have a series of questions. Sometimes it's just a couple, like this time there's 12. And here's a bunch of questions, all right? A lot of these are just significant figures and stuff like that, different kinds of things. But anyway, on the next slide are all of the answers. So again, I'm really big into, cover up the answers, try the problem yourself, and then check yourself, all right? If you do good, pat yourself in the back. If you don't do good, don't panic. Just contact me, talk to the Learning Success Center, Abbott Center, or stuff like that. In addition to all of that, on the website, there are, I have to make sure I use the right terminology, this chapter, there are, what did I call it? These are chapter guides, study guides, concept guides, chapter guides, I'm sorry. On the website there are chapter guides. The chapter guides are just lists of all the digital things that might help you on the website. The web group is all over this, but you can use them too if you'd like. So I have like some study materials and stuff that are there. So lots of ways that you can hopefully learn the material. Any questions on that stuff? We'll think this started because that's kind of the boring chapter. Chapter 1 is kind of like the first level of a big building. And when you come in, all right, you look at where the different people are in the building and, oh, I need to go to level 5 or, oh, I need to go to level 8 or whatever, all right? And there's probably restrooms, I may be a coffee place on the first floor, but it's not that exciting. Most of why you went to the building in the first place is probably one of the higher levels. And that's how I feel about that chapter. Chapter 1 has a lot of the really important things, temperature conversions and density and metrics and sig figs, of course. But now we're actually getting into the chemistry, which is really, really cool. In this section, we're going to focus a lot on what the periodic table is. And along the way with the periodic table, we'll talk about elements, how they're different from compounds. We'll talk about how the elements, some of them like to lose an electron. You can see the ones on this side of the window are all positive. On the other hand, some of them like to gain electrons and become negative, and those are the ones on the other side of the classroom. And you can see the poor teacher here, remember you told me what's out the window that's so attractive. There's a really strong interaction between positives and negatives, all right? It's a kind of glue that holds the atoms and molecules together. And that's something else we'll talk about, like what is this glue? Why is there an attraction between positives and negatives? So all this stuff will be in this section. Now, the next several chapters are really kind of mixed together. And so for this section, I'm going to say that it's over chapter 2 and a tiny bit of chapter 3. Now, some of the stuff of chapter 2, we're going to look more in the next section. So that's why I'm calling this section chapter 2, part 1, and the next one is chapter 2, part 2. But then we skip to chapter 4, part 1, and chapter 4, part 2. So I don't really have a chapter 3 in there because it's mixed together. And I apologize for the confusion, but hopefully you'll see why this is all happening. So without further ado, we're going to look here at chapter 2, part 1. And again, chapter 2, part 2 is next. And chapter 3 will be interspaced over these different sections. Crazy instructors. Any questions on this kind of? All right. So, atoms and elements. Never trust an atom. They make up everything. All right, I know. Keep my day job. I'm not a good Atoms literally are the building blocks of everything. We talked about that. So when I said they make up everything, they literally make up everything. They're not making up like, okay, prof that really on. When I say prof that on, it means that once in a while I get off target and Yeah, brought that back. Come on. Anyway, elements. Periodic table lists all the building blocks for everything known, all right? Everything in the universe, from the sun to the little ant that crawled across your table maybe the other day, to the sugary candy that maybe the ant was looking at, whatever, all right? They literally are the building blocks. Now, elements are kind of the bulk description. Atom is the smallest part of the element. We'll talk about that here in a little bit. These little graphics right here show kind of a representation of what hydrogen and oxygen look like. And if you look at these two things, first of all, you can tell that oxygen has more volume. It's bigger, all right, than hydrogen. You can also tell that this blue shimmering stuff is smaller here than it is there. Also, the middle part right there, which we're going to call the nucleus, you can see that the oxygen nucleus is bigger than hydrogen. So when scientists have sat down and thought about what the atom is, there are three what they call subatomic particles that go inside each atom. And the ones that we're going to talk about here as chemists are the proton, the neutron, and the electrons. Now, the protons and neutrons are both inside the nucleus right there. And the electrons circle, quote unquote, around the outside. And as I talked about last Monday, I think, they don't really circle, and we're going to talk in Chem 221 more about what they're doing. This shimmering kind of blue cloud is more of what they're doing, and we'll talk about it. But the other thing I want to talk about is that in these pictures, you know, the atom looks more spherical than not, and that's good. But in the middle, all right, you can see the nucleus, all right? The nucleus is where the protons and electrons are. If you remember from the powers of 10 video I showed you last week, there were several powers of 10, several orders of magnitude between where you got through the electrons and where you could even see the nucleus. So these are great teaching models to show you where the nucleus is. But in your own mind, the nucleus is like so small. I tried to make the smallest dot possible right there, and even that really is too big. The nucleus is way smaller than the atoms that are around it. So realize that these are teaching illusions, okay? In reality, the nucleus is quite a bit smaller. So atoms contain protons, neutrons, and electrons. Protons and neutrons are in the nucleus. Electrons, quote unquote, circle around the outside. Okay?
If modern astrophysical theories of the origin of the universe are correct, in the first few moments of the violent birth of the universe, there were only two elements, hydrogen and helium.
The model for how all this came to be, all right, in science started with the Big Bang Theory. All right, it's not the cheesy sitcom that was on earlier, but anyway, the Big Bang, they think, was basically like everything swished really tight together, and then bam, and then all of a sudden then matter was dispersed out. And there's lots of theories. The universe, they think, is about 13.77 billion years old, and that number, of course, fluctuates as new models come out. But for us here in chemistry, the important thing is that we didn't instantly have like everything that we have in this classroom. We basically took a while, but then finally hydrogen began to appear, which is the simplest of the elements, and then helium, and then we started to get into other ones like lithium and carbon. But it was kind of a slow process. It didn't happen right away, and we'll talk about why that is here in a little bit. Carbon, oxygen, and neon were some of the atoms that came next. And I skipped some elements there. For example, fluorine, which is F, and beryllium, which is Be. Some elements were more abundant than others. And that's an ongoing area of research, like why some elements are in such higher abundance than others. And that's an interesting thing. But if you think about the entire universe, all right, like if you were looking at the whole universe as a cell, you'd say, oh, that's a hydrogen universe. Because hydrogen dominates the abundance when you think about all the sources around. And if you think about the sun is huge, all right? And there's a lot more hydrogen in the sun than anything else, and that's how most stars are. So it's kind of cool here on the Earth that we have not just hydrogen, but we also have a lot of other elements and stuff to do things, i.e. live, all right? So it's a good thing. Anyway, I digress once again. All the elements have some similar characteristics and some differences, but one thing you can probably see is that some atoms are certainly smaller and some atoms are bigger, and that's across the way. But all of the elements, whether it's carbon, oxygen, hydrogen, or uranium, they all have protons, electrons, and neutrons inside them. And that's what we'll talk about in this chapter, is what's going on. Any questions on this week? This is the cosmic abundance, all right? And you can see as the red value or brown, whatever it is, get bigger, that means you have more and more of the elements. So you can see that in the universe, hydrogen is by far the biggest. Helium is pretty close, but hydrogen is quite a bit larger than anything else. And notice how there's not a lot of lithium or beryllium, but there's a pretty good amount of carbon and oxygen, and there's actually an amazing amount of iron. And we're going to talk about why iron is so abundant in Chem 222. But for right now, just realize that in the universe itself, there's a different amount of elements, like you don't have equal amounts of everything. Now, on the Earth, people will talk about an elemental abundance of the crust, which is, of course, the ground, and also in the atmosphere. So in the Earth's crust, there's more silicon and oxygen than anything else, all right? The core maybe has iron, but to the best of their ability, silicon and oxygen are most. And in the air we breathe, most of the air we breathe is actually nitrogen. It's the oxygen which gives us life. Thankfully, that's the second most abundant, woohoo! But nitrogen is actually number one. This slide also gives me a chance to introduce what I think is one of the coolest websites on the internet for chemistry, and it's Webelements.com. And Webelements.com has lots of information, like this information of abundances, but it also has a lot of information on each one of the elements. And when you pick a class presentation element, all right, you can go to Webelements.com, you see like a periodic table, you click on your element, we'll say it's chlorine, there'll be a lot of information there on your element. And you certainly don't have to use Webelements.com, but it is pretty handy if you're interested. Now, in the old days, all right, people didn't know what was happening in chemistry, but at the time of the Greeks or so, people would, sit around their campfires and too early for bed. So anyway, they would start talking about things, and one of the things they talked about is what is the nature of matter, all right? And Aristotle is usually given credit for it, but it's actually this Empedocles, I'm not sure how you say his name, but anyway, he came up with the idea that there are four types of matter, and he called them fire, water, earth, and air, all right? And he actually used the term elements, all right? Well, Plato did and stuff, but anyway, for these four elements, and this was the model of chemistry for about 2,000 years, which is just crazy. And for a while, they expanded on it, and a mixture of air and water is the wet property, and like earth and fire is dry, etc. And this is kind of a funny joke. The old periodic table, all right, and it's just got the four elements: fire, air, water, and earth. I find this amazing. I also find it very frustrating, because this theory of atoms, all right, proposed by, or theory of matter proposed by these gentlemen, dominated scientific thought in chemistry for a long, long time, and it didn't help things because it was pretty strange. Unfortunately, while these guys were talking, and I believe it was around Athens and Greece and stuff, so a major area, there was another person, and his name is Democritus. And Democritus, who was a contemporary of Plato, all right, had his own idea of what matter is. And it's really interesting. They feel how Democritus came to it is he had like a thing of gold in front of him. And he goes, well, if I cut the gold in half, I'll have two equal amounts of gold. And then I'll take one of those halves and I'll cut it in half, so I have two halves. Cut. Well, finally, you're going to get down to the smallest piece of gold, which still has properties of the bulk gold, all right? And he called them atoms. And atoms and stuff are the smallest pieces of any element. If you cut the atom, then he said, then it's no longer going to be gold, all right? And the smallest thing is this atomos, or atoms, and that's where we get the name atom, by the way. Now, he was way ahead of his time, and it's really unfortunate that they didn't take his theories and run with it. But of course, they didn't have any idea. Apparently, Democritus was kind of from more of a backwater in Greece. It wasn't as sophisticated, I guess, as other places. And this is like, oh man, no, that this gold is one solid piece. And he says, no, I believe everything is made up of tiny particles we can't see. So he was way ahead of his time. They didn't follow him up. Darn it. But he is like kind of a hero, if you will, of modern chemistry, because wow, he really nailed this. And even some of the subsequent theories, which begin to break out of Aristotle's four-element idea, didn't have some of these properties in there. So he's kind of a cool person. So there's a comic book that took this anyway. All right, I need to get out more, I know. All right, skip a lot of years, all right? And we finally get then into the 1700s, 1800s. And around this time, that's when Newton developed, calculus and stuff like that, started getting things going. But chemistry had a slow evolution. There was a little bit of alchemy, all right? Alchemy is a way they were trying to make gold and stuff like that. But it wasn't like officially a scientific thing. However, this guy named John Dalton came on the scene, and through a whole series of investigations, he proposed what he called the atomic theory. And so sometimes you'll hear John Dalton referred to as the Newton of chemistry. Newton was really instrumental when it came to physics, all right? He had a lot of the ideas going, as well as math. Like, he basically did calculus himself, and he was an interesting person. So the equivalent Newton, if you will, for chemistry is sometimes seen as John Dalton. And John Dalton was hardly perfect, but he did at least bring chemistry into the area where you actually had a field of science to study. So in John Dalton's atomic theory, he made some proposals. He said atoms cannot be created or destroyed, all right? And we're going to see that's not totally true, but it does have some application. Now, this one's important. Atoms of one element are different from other elements' atoms, all right? So what that means is that somehow a hydrogen atom is different from helium, and a helium is different from lithium, stuff like that. This was important, and he proposed a scale to measure these atomic masses. We'll talk here in a little bit about what's called an atomic mass unit, and it's just a really, really small number of grams, all right? So just like the pound is a unit of mass, it's about 454 grams, atomic mass unit, 10 to the minus 24 grams. So this is not just small, it's freaking small, all right? It's really, really small. The Dalton is a unit that means 1 AMU. So sometimes in some books you'll hear instead of AMUs, they'll talk about Daltons, DA, capital D, little a. It's in reference to him because he was the first one to propose that maybe you could put these things on a scale. And in this time frame, they didn't have those kind of scales, all right? But he proposed that one day there would be one, and sure enough, that was a pretty good call. Chemical change involves bond breaking, bond making, and the rearrangement of atoms. And this one's pretty important too. People in alchemy were thinking that you had entire transformations of things. So if you could make gold, you'd make it from some kind of other stuff into gold. But what Dalton said is all those atoms are present both at the beginning and the end. And it's only through their rearrangement, bond breaking and bond making, then that molecules begin to form. And no one had really thought about that before until Dalton's time. Now, he didn't include Democritus' ideas that atoms have structure. He thought maybe these were like really small points of light, if you will. And that's okay. I mean, it wasn't right. It's okay. The other thing is that he said atoms can't be created or destroyed. And, you know, atoms can be created or destroyed. That's the nuclear bombs and stuff like that, nuclear power. You can make and destroy atoms. But it's a very high energy process. And here at Mount Hood, even in the 21st century, it's not impossible, but it's very difficult for us to create atoms or destroy atoms. We do have some stuff in our chemistry lab that can make it happen, but it's not a simple thing. So I don't hold this one against him because it's a pretty high energy process. But anyway, you can see how we got some beginning parts here now of like what chemistry is all about. Any questions?
An electroscope is a device used to detect electric charges. If we induce a charge in a rod and then touch it to the electroscope, the leads in the electroscope become charged and separate. The experiment demonstrates that like charges repel one another.
Ben Franklin, as well as people like Michael Faraday and stuff like that, started looking into what's called electricity. And electricity is another tool we're going to use a lot in chemistry. And in electricity, they basically found that you can have positive charges and negative charges. So some substances create then these charges, and there's things you can do with them. Now, this is important. The opposite charges will attract each other, and the like charges will repel. So if you have a negative and a positive ion, there's going to be an attraction. They're going to come together, all right? On the other hand, negative and negatives repel, positive and positives repel. And this is the joke how in romantic relationships, you know, you always attract the opposite person that you want, because but anyway, that's Ben Franklin and not necessarily applicable, but anyway, like people repel each other. Doesn't matter. Charge is conserved. Conserve is an important concept. Conserve just means that you don't make or lose any charge. A lot of times in chemistry we'll talk about how mass is conserved, and that just means that the mass that goes in equals the mass that comes out. You can have mass rearranged to new compounds and stuff, and energy can be released, but the overall mass is conserved. In these problems, the charge is conserved. The number of positive charges doesn't change, the number of negative charges doesn't change, but you can rearrange them along the way. Another thing that's really interesting is that the positive-negative attraction, the force between them, is inversely proportional to the distance. So we'll say that you're a positive proton and I'm a negative electron. All right, right now, pretty good force, but as I get farther away, the amount of attraction between the positives and negatives go down. And so like here, it's like, you know, pinkies, we can hold on. I would shake your hand normally, but I'm not doing that. I know, freaking COVID. But, all right, pop that back on. So I'm moving away, pinkies, and then finally, they break, and then we're apart. So there's always going to be a place when these positives and negatives where there's no more attraction. They get closer, it gets stronger. They get farther away, the force gets weaker. Questions on any of that? Now, another thing we need to talk about to make sense of everything is radioactivity. And radioactivity is kind of a fascinating subject. We'll come back to this in Chem 222 more. But anyway, for what we need to know right now is that when they first figured out about radioactivity, this guy named Becquerel, Henry Becquerel, he realized there was some kind of a ray coming from these samples of ore. And I've been told, all right, that he had this ore from some mine, and he sat it down next to some photographic plates. And in the old days, photography plates, it's not like ones on your camera, they would have a silver, kind of a nitrate, a silver emulsion on them, and as the light came in, that's what would make the image. Well, these rays from the ore went through the container that the ore was held in, and they also went through the protective things that kept the photography plates like isolated from the sun. So something was going through layers of fabric in order to make these plates exposed. And they did more studies on it, and they thought, aha, these rocks, which have uranium, they know now, have some radioactive materials in them. These rays will go through many different objects as if they're not there. They're so high energy that they're hard to stop. And if you do have a photographic plate, which is basically like a piece of film, kind of, all right, but bigger and old school, which is basically a silver thing, the silver will react with these rays as they come through. It makes like a smudging kind of an effect. It was hard to figure this out, and it was a little bit coincidence, but Becquerel is the one that's given the credit for discovering radioactivity, and the ray is where the radioactive comes from. But anyway, Becquerel is cool, but Marie Curie really rocked this field, and Marie Curie is just awesome. She is considered sometimes the Newton of radioactivity. So Newton, again, started physics and calculus, all right? Arguably John Dalton is the Newton of chemistry. She is the Newton of radioactivity because she really expounded on a lot of what radioactivity was all about. And she realized that, these substances, the ore itself, is actually disintegrating, and you end up creating these rays, which is where the radioactivity thing came from. Now, Dalton thought the atoms were indestructible, although Democritus thought maybe you could change one. So Marie Curie basically said, I'm sorry, Dalton, but we got to go a little further here. Something is literally breaking down to create these radioactive beams that are coming out, all right? And that's more in line with what Democritus thought, which was kind of cool. Marie Curie was a woman in a male-dominated place in France, and they kind of weren't super happy to have her there, so they made her work out in a shed, and the shed got super hot in the summer and super cold in the winter, and she had to go through kilogram after kilogram of material just to get small amounts of her radioactive isotope. So if you ever want to read about someone who's pretty cool and pretty motivating and stuff, there's stories of Marie Curie's life that are pretty cool. Anyway, through all of her work, she realized there's actually different kinds of rays, and they named them alpha, beta, and gamma. And an alpha ray, or an alpha, is nothing more than a helium atom that's supercharged. Now, this term right here is called cation. We're going to use it more in the next chapter. A cation is a positively charged atom. So an alpha ray is a positive helium atom. But if you've ever been to a birthday party and you suck up the helium and you're like, oh, now I talk like a squirrel. This is not the kind of helium you want to do that with, man. This would like kill you. It's like super high energy. It's like it's like a meth or something. No, 10 times meth. It's really powerful. It's very high energy helium, all right? And when this comes out, you want to get away from it. This is the symbol for alpha. It's a lowercase alpha in the Greek alphabet. And sometimes you'll see this referencing alpha charges. Notice that because it's helium, it's a particle, all right? It is like, it has mass and stuff. We'll talk about that here in a little bit. Now, in addition to alpha rays, there's also beta rays. And beta rays are supercharged electrons. Now, we're going to talk a lot more about electrons. But these aren't the electrons that we'll talk about normally. These are like, again, supercharged on meth. I don't know if I like that idea, but that is kind of working for me right now for some reason. Anyway, supercharged electrons. These aren't the ones we're going to use to make molecules later on. These are going to be ones that will cause damage. This is the beta symbol. It's lowercase beta in the Greek alphabet, so we'll see that sometimes. And then some of them also release gamma rays. And gamma rays are just high energy beams, kind of like a beam of light. So for example, when I use my pointer there to circle the gamma symbol, all right, that's just a beam of light. I'm using it from my little pointer here. That would be the closest to the gamma ray, all right? But if I could do this with a light, I wouldn't dare do that with a gamma ray. The gamma ray would just rip through the thing and probably would burn a hole in my screen and stuff like that. Alpha and beta have mass. You can actually weigh them. But gamma, on the other hand, has no mass. It's just energy. And like I talked about earlier, a cation is a positively charged species, so alpha rays have charge. Beta, we're going to see electrons are negatively charged. So alpha and beta have not only mass, you could put them on a scale and weigh them, but they also have a charge. But gamma rays, man, they have no mass, no charge. They're really hard to stop. All right, it's like beaming a light at something and stuff. Questions on? Okay.
When passed through charged plates, radioactive emissions split into 3 distinct rays. Beta rays are negatively charged. Gamma rays have no charge. Alpha rays have a positive charge.
This is how they detected these a long time ago, which I think is really cool. They used something that was super radioactive. There's an element called radium that works really well for here. But anyway, when you have a sample of radium, the electricity comes off 360 degrees all the way around, up and down, stuff like that. So in science, oftentimes they use what's called a double slit. And the double slit just takes that wide angle beam and makes it into a narrow plane of radiation, all right? All the other pieces kind of bounce off, if you will. After the double slit, they put it through a set of charged electric plates, and plates have a positive and a negative charge. And what they found then is that these things split. This, by the way, is a piece of film, all right? And they put it out there. So they turned this on for a little bit. They then developed the piece of film, and they said, whoa, they had 3 like smudges, if you will, on their piece of film. And one of the beams went literally straight on through, all right? It wasn't affected by positive or negative charges. And that's the gamma ray, all right? And the reason the other 2 split off, beta rays are negative. Negative charges go towards positive things, opposites attract, we talked about earlier. On the other hand, the alpha particles, or alpha rays, have a positive charge. They're going to be attracted to the negative plate. So you can see that the alpha went off a little bit to the left, the beta went off a little bit to the right. The reason the beta went off more is beta, we're going to see, is a lighter type of atom than the alpha. And if it's lighter, you can move it more than if you do the heavier alpha ray and stuff. Now, when it comes to radiation, all right, people have to be really concerned with safety. And for example, if you have an alpha ray, all right, and you fire it at a target, alpha rays, because they have mass and they have charge, and they have a lot of mass, by the way, they're usually stopped by things like paper, all right? So if you had an alpha ray gun, and you aimed it at me, darn you, Russell, all right? I think my clothes would be good enough to protect against alpha rays. So unless you got the alpha beam in my eye or mouth or something like that, I would be okay. It doesn't take much to prevent alpha rays from going through. Now, on the other hand, beta rays are also massively in charge, but they're smaller and they're a little bit faster usually. So they will usually go through things like papers and clothes. A little bit of lead, though, will definitely stop those. Beta rays are usually stopped by your skin, all right? So knock on wood, most of the time, your clothes will stop most of the alpha rays and your skin will stop most of the beta rays. But man, when it comes to the gamma particles, I mean, there's no mass, there's no charge, and they have a lot of energy. So they just rip right on through things. So like if you were to fire a gamma gun at me, I would run. I'll be totally honest. I will run as fast as I can, because most of the time what you need is you just need distance between you and the source to keep it away from you. They're really dangerous. They go through a lot of things. If you have enough lead or something very dense, you can stop it, but it's not exactly always the easiest. Okay, so here's kind of a silly question, but it does help you to kind of think what's going on. If you take a piece of silk and you rub it with a glass rod, all right, that's a way to create a charge. And in this case, it creates a slight positive charge. So knowing here about the type of radiation, it says which type of radiation would be attracted to your glass rod. So if you have a positive charged rod, one of these will do it. It's not none of the above, all right? Cosmic rays are actually a different kind of radiation. They're from the sun. It usually involves big particles being ejected from the corona mass. Created the Fantastic Four. Woohoo, if you're into that kind of stuff. Anyway, cosmic rays, not appropriate here. We didn't talk about them. So of alpha, beta, and gamma, Which one of those had no charge? Gamma. Well done. That's right. Gamma had no charge. If something doesn't have a charge, it's not going to care if you have something positive or negative or neutral. It's going to totally ignore it. So it's not going to be the gamma radiation which is attracted here. Now, when it comes to these two, are we looking for a type of radiation that has a positive or negative charge? Remembering that our rod is positive. That's right, we want the negative one. Opposites attract. So if our rod is positive, we want the negative. Which one of those two is the negative radiation? Beta, that's right. So probably then, of these types of radiation, the beta rays, the beta radiation, would be the one that would be attracted to the positive glass rod. Opposites attract, all right. The rod is positive, beta radiation is negative, so those two should have a little bit of a difference. One final thing on Marie Curie. She's just phenomenal. She's the first of the chemistry cool people that we'll talk about in this class. But anyway, she actually discovered two elements by herself, which is really cool, both radium and polonium. Polonium she named after Poland, which is where she was from. Radium from the rays that come from it, from the radiation. In 1911, she isolated pure radium, and which was just crazy. She bought some, but she also was able to isolate it from them. And again, nobody was helping her at the French University, which is kind of sad. And they continued to not support her, even though she did all these cool things. So in 1919, this group called the American Association of University of Women, which is still, by the way, around, they actually raised $150,000. And in 1919, that was a lot of money, all right? That allowed her to buy 1 gram of radium, the element she'd isolated herself, by the way, so she could continue her work. And I thought that was pretty cool. She actually died of leukemia. Leukemia is from things being exposed to a type of cancer. She was killed by her work. But she has a lot of cool quotes. This is one of my favorites. Nothing in life is to be feared, it's only to be understood. She's a 2-time Nobel Prize winner, which is kind of cool. 1 time by herself and 1 time with her husband Pierre, as well as Becquerel, so it's kind of neat. Questions? All right, let's take a 5-minute break. It's about 9:55. We'll start back here about 10 o'clock. So stretch your legs and stuff.